Hello, everyone, and welcome to this Oracle Cloud World presentation on MySQL HeatWave Lakehouse. We'll be talking about scale-out load and query performance. My name is Abhinav Agarwal. I am a Senior Principal Product Manager with the MySQL HeatWave Development Group. And I have with me Gaurav Chadha, Senior Engineering Manager, also with the HeatWave Lakehouse Development Group. I do want to point out that what we are talking about is a pre-release product. So do take a minute to go over the safe harbor statement and also the fact that we'll be talking about functionality that is not currently GA. With that, now let's talk about MySQL. Before we get into HeatWave and Lakehouse, let's spend a minute or two talking about MySQL. So you all know it's an extremely popular database. And how popular exactly? In fact, it is the world's most popular open source database. If you're familiar with DB Engine ranking, it is widely used and followed, and it uses a variety of criteria and metrics to come up with a list of the most popular databases. The most popular database according to the ranking was the Oracle database, followed by MySQL, which is the most popular open source database in the market. And not just that, it continues to see wide interest and adoption and use by the developer community across the world. This is reflected in the use of MySQL across the world, across almost every single industry and some of the biggest companies that exist out there. I won't go over all the names, but as you can see, virtually every large company is represented on this slide. Now, one of the things to keep in mind is that MySQL is an amazing open source database for OLTP applications. If you want to run analytics on a database like MySQL, pretty much the same kinds of challenges are going to be faced by you as you face with other OLTP applications. Namely, you have to spin up an ETL process, you have to create another server where you have to have another analytics optimized database. You are not going to get real-time analytics because there's going to be a lag from the time data moves out of your OLTP transactional database and then into your analytics database. And then obviously you have all of your governance and data governance and compliance and auditing costs that have to go in now for the second database. And all of this means that apart from the fact you're not getting real-time analytics, it's adding to the complexity, it is adding to the costs. MySQL HeatWave was developed exactly to address all of these challenges that we saw in the previous slide. One single database that performs the tasks and functions of two databases, namely transactional and analytics. It is one service that runs for both OLTP and OLAP. You don't have to have any ETL taking data from the transactional database and piping it to your OLAP database. All of the data that you want is available in memory, which means you get very fast query performance. The cost is a fraction of what you would end up paying if you were to go in with any other solution out there in the market. Real-time analytics, because changes made to your transactional database are propagated in real time to your HeatWave in-memory query engine. It is one database service, so therefore you don't have any additional security implications. And very importantly, all of your existing market-leading analytic applications such as Oracle Analytics Cloud and others work as is with HeatWave without having to make any changes. So before we get into the next part, just for reference, I want you to spend a minute and take a look at the slide that not only are we very fast, but we are faster than anything that exists in the market today. So our benchmarks have shown us to be thousands of times, literally not hundreds, but thousands of times faster than AWS Aurora. And even if you look at some other vendor like Snowflake, you'll find that our ROI is almost 35 times what they claim to provide. But let's look at a couple of challenges in the world of data that have emerged in the last few years, right? There are three challenges specifically. The first one is, and it's not a surprise to anyone, that the amount of data being generated has been growing literally exponentially. And 175 zettabytes, according to one estimate, is a number that we don't even know how to wrap our heads around. But the more serious implication is that most of this data is semi-structured or unstructured data. And a consequence of that number is that most of this data is not flowing into traditional databases, but into object stores. And the final point to note is that a very, very tiny fraction of this data is actually being used for decision making, which begs the question that if you are collecting so much of data, but you're not using it to drive your decision making at your organization, then that data is not really serving its purpose. So why do we have this disconnect that where data is increasing? Why can't you make use of the data for decision making? And there are 3 or 4 points to keep in mind there. The first one is a lot of this data that is being generated is unstructured or semi-structured. Now, if you look at how data flows into traditional transactional databases, it is very, very well defined. There's a very well defined schema on top of it. The data is structured. You know your tables, your relations, your columns, your data types, all of those things before it even enters your data warehouse, which means that you know your schema when you write to the database. The third point is that beyond a certain point, it becomes fairly expensive, cost prohibitive to keep on pumping these zettabytes of data into your traditional databases. They were not built to handle these kinds of data volumes. And anytime you want to make changes, even if a single column gets introduced, you have to go back in and pretty much rework parts of your ETL process and your data warehouse design. So all of these consequences mean that if you are going to be relying only on traditional databases to do your analytics, it is not a very practical solution. So to address that challenge, we in the MySQL HeatWave group have come up with what we call the Lakehouse. So one single database to handle 4 types of challenges. First one we have already talked about, which is to address the fact that you have a traditional transactional processing database in MySQL. The second challenge that we solved was to make it the database of choice for analytic processing also for all of your MySQL data. The third challenge that we solved was to also make it a single platform for all of your machine learning needs. So the introduction earlier this year of HeatWave machine learning addressed that. And now with Lakehouse, what we have introduced is the ability to go against object store data, which is where these massive amounts of data are being pumped into. And not just object store data, but if you have data sitting in other clouds, and if you pipe them into your object store, you can even make use of those data sets for your single unified processing. So what does MySQL HeatWave Lakehouse provide at a high level? If you were to look at it, there are 4 or 5 things to keep in mind. First one is, just as HeatWave is your single unified query engine for your transactional OLAP and machine learning needs, Lakehouse adds object store data also to that same unified single query engine. Next, we have a very, very interesting feature as part of Lakehouse called Autopilot, and it works just as well as it has with HeatWave as it does with Lakehouse. The next point, remember that data volumes have been increasing exponentially, right? So any analytic engine, product, or service that claims to solve these needs has to be able to scale out. And we are not talking about running your analytic database on 1 to 10 nodes. We are talking about running it on literally hundreds and hundreds of nodes. And most importantly of all, it works with your standard MySQL syntax. You don't have to write specially constructed queries for it. If you can write standard MySQL queries to get data out of your databases, out of HeatWave, out of DB, you can do the same with Lakehouse. So One of the very interesting things, and we'll look at that in more detail in the coming slides, is this concept of so if you look at this query at the bottom of your screen, you will see data coming in from a traditional MySQL database as well as from an object store data source, right? So you create an external table that points to data resident in object store. You already have data resident in your traditional transactional MySQL database, and using a single query, you can join data from these two data sources into one single result set. So let's now drill one level deeper into the details as to how we make all of this possible. And at this point, I'd like to introduce and invite my colleague Gaurav Chadha to walk through the next set of slides. And Gaurav, one of the very very interesting things is the way when you talk of going from a few terabytes of data to literally hundreds and hundreds of terabytes of data, there are certain challenges that come to mind. Love to hear how we have solved those challenges.
Thanks, Abhinav. Yeah, it has been an interesting journey to get to here with Lakehouse. So, diving a little deeper, in a nutshell, HeatWave Lakehouse is an in-memory query processing engine for data that is stored in object store. This data can be structured and relational, but can be present in different formats like CSV or other open formats like Apache Parquet. And once we load it into Lakehouse, we can query this data, which has never been present in any database storage. To do so efficiently, though, all source data is first read and transformed into the HeatWave format. This is a hybrid columnar format, which helps us do analytical queries very efficiently in a performant manner. This transformed data is kept both in memory for good query processing, as well as stored back into object store for fast recovery. A unique capability that we added with Lakehouse is to be able to infer the schema of the data we're ingesting. So remember, this data is not stored in a database, so it may or may not have a schema associated with it, any metadata. So we are able to infer the schema while loading this data or even before it, and obviating the need for the user to provide that as input. Now, through the rest of the talk, we'll go into details of how we attack each of these features and problems and challenges we face. So one of the biggest challenges we face with Lakehouse is due to the immense scale of this system. Going from the traditional HeatWave data warehouse to Lakehouse, we have an order to couple of orders of magnitude increase in data up to 400 terabytes. And to manage all this data and query it efficiently, we have also increased the size for cluster by a similar scale to as much as 512 nodes. So how do we manage and load this data in a performant scale-out fashion? Let's start with what HeatWave has today. It ingests data from MySQL InnoDB database and converts into the internal HeatWave format and populates the HeatWave cluster. That's what exists with HeatWave data warehouse today. Now, for performance reasons and faster recovery, this data that we just transformed and stored in the HeatWave cluster is also backed up into object store. But with Lakehouse, we have another dimension, as Abhinav mentioned. We have larger and larger amounts of data being stored in object store outside of traditional databases. And so we can have this data in different formats, but also we can have data in other databases, take their backups, and put it in object store. This kind of data can also be ingested by Lakehouse. To do this efficiently, we have designed a new module, which we have named Heat Pump. So Heat Pump You can point heat pump to these new external data sources lying in object store, and heat pump will, in a fast and scalable fashion, load this data, transform it into the internal HeatWave format, which we've talked about, and store it back into object store for a similar reason as for warehouse, which is faster recovery. While loading this data, it also collects statistics on the data. Its NDV, its average column length, and other many statistics. These statistics help with uh, inferring the schema of the data. It helps with query plan improvements, which we'll go into later. So putting this together, in Lakehouse, we have an external table which is defined using the sources which are in object store. And the primary engine for this is a new one that we call data lake. So the HeatWave data lake is the primary engine for these external tables. However, this is not a storage engine like InnoDB. Instead, it is an interface for the external tables and its data in object store. We are able to provide an extensible interface, very similar to how we create and alter tables in MySQL today. Using a JSON-like interface, you can specify where the data is stored. It can be split across multiple buckets in different regions. And once the table is created on a secondary load, we call this module, which we just talked about, heat pump. So heat pump loads, transforms, and analyzes this source data. It runs on the same cluster as the HeatWave compute. It is a part of the HeatWave cluster. And obviously, as you said, while reading it, it will transform this data from different source formats into our internal format. One of the biggest tasks that heat pump has to perform is to be able to load this massive amounts of data, hundreds of terabytes, in a highly parallel and efficient manner. To do so, let's go over the data flow of how heat pump loads this data in parallel fashion. As we just mentioned, in the create or alter table statements, you can specify where the data lives. Once we have that, we can list those data sources and get its size. And these can be hundreds to thousands to millions of distinct objects stored in object store. Given this list of objects, because we want to do this in a highly parallel fashion, we divide these objects into smaller tasks. And these tasks are typically 100 megabytes big. Now, having divided these tasks inside a node, each thread can work on this task independently of each other. However, dividing this work at a task level granularity can be too fine, so we group these tasks into patches, which can be assigned to nodes. And within a node, each thread can pick up an individual task. Now, the question is, how do we assign these patches of work to different nodes? One simple approach can be we just take the number of patches, divide by the number of nodes, and allocate a fixed number of patches, fixed and equal number of patches to each node. This could be a reasonable approach, given that all the nodes are the same size and capacity. However, the speed or the performance of each node can vary significantly. It can vary because the latency and bandwidth it receives from object store can be different compared to other nodes. It can also vary because it needs to read and transform the data, and the speed of that is determined by the nature of the data, which can vary from task to task, batch to batch. As a result, in a large enough system, we will always have stragglers, which lead to a long tail of slow to finish batches. These stragglers will hold up the rest of the cluster, leading to poor performance. So instead, we we try to dynamically distribute the tasks across the nodes. Um, let's start with the data. So we have the data divided into tasks, which are the black bars here. These tasks are grouped into batches of k tasks each, and our job here is to distribute these tasks across this cluster of compute nodes such that we get the best performance. A static allocation, as we said, does not work very well. So we do our best to distribute tasks dynamically across these nodes. This is essentially a work queue pull-based model where we start with assigning a batch of work to each node. Once a node finishes their batch of work, that node then asks a central coordinator for the next batch of work, and then the next batch of work, and so on. This way, if a node is fast, it can perform more work in the same amount of time as another node which is slow to execute that batch because of a variety of reasons. However, because of this work queue pull based model, we are able to reduce the deviation in the total time each node works. And that's the goal. We want to keep all nodes busy at the same time, um, and not have some number of nodes waiting for others. One key point here is for this scheme to work well, the number of batches we create has to be much greater than the number of nodes to reduce the skew of work across the different nodes. And within a batch of work, the number of tasks being performed by individual threads in that node has to be much more than the number of threads. For the same reason, each thread inside a node will also look for work to do. It will perform one task and then look for the next task to work on. And if the number of tasks is much higher than the number of nodes, then we are able to distribute this work well. Now that we have all these tasks, a central tenet here is that the tasks have to be as independent of each other as possible. And that depends upon the input format. There are many different formats that the source data can be in. Currently, we support CSV and Apache Parquet. One is CSV is a row major format, and Parquet is a widely used hybrid columnar format. So for CSVs, we can start with the row, and as we just saw, we divide the file into different tasks, and these tasks are equal in size. So it can happen that a single row of CSV gets split into two tasks. Let's focus on worker 2, which gets this slice of the line. Now, worker 2 can interpret this line as a quoted comma, or it can interpret it as a quoted string separated by commas. And it is impossible, really, for an independent worker to decide deterministically what the correct interpretation is. So instead, the worker speculates on the initial state, whether the string starts quoted or not, and starts parsing the line. If an error occurs with one approach, it knows that the other interpretation is correct, and then it can go ahead parsing the string. However, if both interpretations are equally likely, rather possible without errors, then we choose the one which is more likely. For instance, a quoted comma is less likely than a quoted string. And with this speculation, our accuracy, as we've seen, is very high, in line with the results reported in state-of-the-art research work. However, it is speculation at the end of the day, and it can be wrong. So we store the results of this speculation in statistics. And after all the data has been transformed, a validation phase is embarked upon, which looks at the choices made, the speculation choices made for each batch of work. And if that is not correct, then we redo the work but only for that part of the data where the speculation was incorrect. And this way we are able to load and parse data in a massive parallel fashion. Parquet, if the source data is in Parquet, it presents its own challenge because the data is laid out differently. However, there is more structure here, and we can parallelize based on row groups, which are present inside a Parquet file. If the row groups are, however, very large, then we split the row groups just like we split CSV files, and we do some speculation and correction of speculation later on. With all these different threads and nodes downloading data in parallel, there are a lot of requests that are going to object store. And there is always an element of how many requests can an object store or any storage service. And which is that limit is not unbounded. To deal with that, we have proposed a novel algorithm and implemented it, which we call adaptive data flow. Essentially, if all the nodes are making requests, at some point, object store will not be able to service them. If it receives more requests than it can service, it will throttle those requests. And this throttling is visible to the application in the form of request failures. One of the big problems with this is that one aggressive application can affect the performance and the request success rate of other applications because they could be sharing the object store resources in the same region. Moreover, the maximum allowed request rate is dynamic. It can vary with the time, the bucket, the region. It can vary from node to node in the same cluster. So just using an advertised maximum request rate and limiting ourselves, which is not always possible or recommended. So instead, in this in our approach in HeatWave, we adapt our request rate based on the feedback we're receiving from object store. So we'll start requesting data at a certain low rate, and we keep monitoring the failures. Using a learning algorithm, if we see that the failures are very high, we will slow down our own request rate. If the failure rate is very low, we will increase our request rate to object store. And using such feedback-driven learning algorithm, through experiments, we've seen that we are able to match the available request rate very closely and reduce the service errors we see from object store. This ultimately results in better availability, performance, and scalability. Having loaded the data, the next key point is, of course, how well do queries perform in this massively parallel large system. And one thing that is key for good query performance is having good statistics on the data. And these statistics, just like the data is loaded in parallel, are collected in a distributed and parallel fashion. Each node will collect its own local statistics while transforming data. And at the end of all transformed data, an aggregation phase is taken upon, which sums up all this data, all these statistics. And at the end of the table load, these statistics are populated in the individual nodes corresponding to the data that the node has, and it's also provided to the MySQL HeatWave plugin. So armed with these statistics, we can make better decisions about query plans and have better performance. And because the statistics are being able to be captured in a highly parallel fashion, they can be more accurate and not encumbered by slow data load. One interesting case study that we encountered was the performance of a group by operator at larger scales. With the same query plan with the same algorithm of developing query plans, it worked very well for a scale of data at 30 terabytes. But as soon as we went to larger data sets, like 100 terabytes, this did not work well. We had huge performance degradations. The reason is the estimates of NDVs, or a number of distinct values, are likely to go wrong with the larger scale of data. for instance, in this example, if you start with assuming a low NDV for the input data, we come up with certain partition sizes of the data such that they're expected to fit in the cache. However, when we start partitioning the data, because of high NDV in the actual data, the partition size can be large. And the partition size is large, it does not fit in cache, and our performance is low. So with Lakehouse, we have developed an online learning system where, while partitioning, if we see that the NDV estimates are off from the actual data, we will rework our partitioning algorithm so that it fits better in cache and memory. A similar technique is also applied for resizing and repopulating hash tables based on differences in NDV estimates. We did some other optimizations to improve our query performance, with some from having large Bloom filters, using system-wide partitioning more as opposed to broadcast joins, and sometimes using all available memory instead of for partitioning, instead of just being a resident cache. The next thing, big innovation with Lakehouse, is enhancements to the existing already excellent suite of autopilot features that we have with HeatWave. As I said, the input data may not have a schema attached to it, so we do a distributed sampling of the data and use a rule-based algorithm to infer this column types and the schema of the data. This can be provided to the user, who can then just use the provided DDL statements to create a table, alter the table, and finally load the table. I won't go into more details before going on to load and query performance. How do these innovations that we described over the last 20 plus minutes translate to load and query performance? So in this experiment, we loaded the TPCH data of 10 terabytes, 100 terabytes, 250 terabytes, and 400 terabytes. As we scaled the data, we scaled the cluster size as well, topping out at 512 nodes for 400 terabyte TPCH. The load time we see scales quite well, in fact, really well, to the extent that for 400 terabytes, we're able to load the data in 4 hours in a cluster, which beats almost every competition out there. And our query performance also scales extremely well with this massive change in data sites, which is a couple of orders of magnitude change in our data set. Again, topping out at a geometric mean of 42 seconds for TPCH on 400 terabytes. Putting this in context against the competition, we can see that we are almost an order of magnitude, or more than an order of magnitude, better in performance and price performance compared to the competition. And with this, I'll hand back to my colleague Abhinav to close out this presentation.
Thank you, Gaurav, for that. A lot of technical details, but I think those are very important for people to understand some of the innovation and the work that has gone in to make HeatWave Lakehouse scalable at the scale of hundreds and hundreds of terabytes of data that we are talking about. So Lakehouse is the next logical step of evolution and innovation in MySQL HeatWave. Now, MySQL HeatWave has already received validation from customers in the market as well as analysts. To pick up just a few quotes from this, right? More Insights and Strategy says that any enterprise looking to simplify the data management and take advantage of running OLTP real-time analytics and machine learning should look at what Oracle is doing with MySQL HeatWave on AWS. And this has obviously also been available on Oracle Cloud. And the benchmarks, right? So the Cube says that these benchmarks are market leading, and competitors very tellingly have chosen not to respond. Taking a look at a few others, the assessment is unanimous from analysts that MySQL HeatWave is very, very compelling. It's very innovative, and it is arguably the best option solution available for customers today who are looking to leverage their existing investments in MySQL. So how do you get started, right? So with MySQL HeatWave, it's available today. You can sign up for a free trial. You can request a guided workshop from your Oracle account manager. You can learn more about it. You can watch demos. You can read white papers. You can read data sheets. You can read analyst comments. You can see what customers are saying by going to oracle.com/mysql. And if you want to give the product a try without signing up for a full-fledged trial, you can actually go to Oracle Live Labs and you can try all of these various live labs that we have for MySQL HeatWave. So all of those will give you a sense of what MySQL HeatWave provides, and that should set you up for wanting to know and adopt Lakehouse when we release it. I hope this session has been useful and informative for you. Again, on behalf of Oracle, I'd like to thank you for watching and attending. I'm Abhinav Agarwal signing off, and thank you, Gaurav, for that talk.